Hi, and welcome again to my Physics Online video lecture series. Tonight's video, I'm going to be talking about self-inductance a little bit. So at this point in the semester, we've already covered Faraday's law, and Faraday's law basically tells us that the magnetic field change, or a change in flux from the magnetic field, can produce an EMF. So we begin with just kind of like a little recall of Faraday's law, and in algebraic terms it says that the induced EMF within a system is equal to negative N times delta of phi b, the flux from the magnetic field, over delta t. And this change could be due to changing the area of the thing that you're getting the flux through, the circuit essentially. Could be due to changing the magnetic field. Could be due to changing the relative orientation between the two of them. But for our purposes, this is more along the lines of maybe just the magnetic field changing. For example, suppose that you have a circuit, and in that circuit you have basically like a battery, and then maybe there's some sort of a load resistor somewhere, and then you have like a switch. So this switch can open and close. Maybe you close the switch so that you suddenly have a closed circuit, and therefore current can flow. Well, this circuit now has some current flowing, the result of which is, if I have current begin to flow, current starts going around like this, and since I now have current, I now have a magnetic field. That magnetic field basically is going to tend to point in this direction throughout this circuit. Strongest at the center, weaker as we get away from the center, more or less. And but you go from B equals 0 over here to B does not equal 0 over here. That means that you've got a change in this flux of magnetic field. Recall that this is negative N times essentially delta of B dot A over delta T. So if I'm changing this magnetic field, B, then is going to cause a change in the flux, means I've got an induced EMF. So simple circuits do this when you turn them on and off. Now, with that said, more complex things like a solenoid, where we found that the magnetic field is given by the amount of current, once again, but also related to like number of windings and that kind of thing. Those will tend to have a larger change in flux when you suddenly turn current on and turn current off. And so this fact that you can have a change in flux due to turning on or off current within your circuit, this is what's sometimes called inductance or self-inductance. You get a self-induced EMF, and it sort of resists your change in current. It's called back EMF or back current. And it is, again, related to the Faraday's law via this equation, but these terms are kind of cumbersome to have to monitor. Like, it's easy to stick an ammeter in a circuit and measure current. It's reasonably easy to stick a voltmeter into a circuit or across an element in a circuit and measure voltage. Like, those things are straightforward. Measuring magnetic field, you have to have a Hall probe, which doesn't really go well with the circuit and ends up having to probe magnetic field in one location. You really need to know what the magnetic field is for the whole area. Where I'm going with all this is that your induced EMF can be given, rather than that previous equation, by essentially a new term which we call self-inductance times the rate change in the current. And again, recall that even in this simple scenario, there is a change in current which is producing this magnetic field that wasn't there before, thereby producing a change in flux. So this new idea is we define what's called self-inductance for a circuit or for a circuit element, and that self-inductance then relates this induced EMF to a change in current, or a rate change in current, rather than to a rate change in magnetic field flux. So the basic process with this, and I'm going to box this equation, this actually defines self-inductance. So this is not just an equality, it's kind of like a definition for average self-inductance. The basic process here is that you want to find what is the self-inductance for a given element, and then from that you're able to get the induced EMF for a given scenario. And how you go about finding that self-inductance is essentially you ask, all right, well, if I were going to change the current, how would that affect the magnetic field? And then how would that in turn affect the flux from the magnetic field, thereby determining the induced EMF via Faraday's law. Put differently, this definition for the self-inductance, it's a good definition, but it's not how we usually go about actually using the self-inductance. It's not how we go about predicting the self-inductance, per se. In a similar way to how we defined capacitance as charge per unit voltage, and then went about asking what properties of, say, a parallel plate capacitor will affect the capacitance, so we want to do with self-inductance. We've got a definition here, but we want to know like what's going to actually determine the self-inductance. That self-inductance should be determined for a given element by maybe like geometric considerations or other set parameters. So to go with this basic process, let's consider a solenoid. So we introduced solenoids in a few videos ago. Basically what you have is this wire that's been wound round and round and round and round like so. And you know that from a cross-sectional view you have a magnetic field. Let's just go ahead and use blue for that. That the magnetic field is more or less uniform inside of the solenoid. It's not a very good drawing to illustrate that, but you know, here's my magnetic field inside the solenoid, more or less uniform in here. Outside, maybe not so uniform. And we know that this magnetic field B is given by mu naught times N times I, where N is defined as the number of turns per unit length. So in those terms, this right here would be the length L, the number of turns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so in this case, N would equal 10, and the length would be however long this is. So, okay, that has related magnetic field to current I. So if I have flux for the magnetic field, phi sub B, that should be B dot A times, again, the number of turns. And so if I want to get delta phi by delta t, that is going to be n times b dot a. I've kind of, maybe I should say n times phi is this, and n times delta phi delta t is this. So this is just finding the flux for one coil and then multiplying by the number of coils. Okay, and so this is B. So if I have a change in the current, so delta I over delta T, I could solve this for I. I is equal to B over mu naught times little n. So if I have delta I over delta T, that should look like delta B over delta T times 1 over mu naught little n. Okay, so coming down here, delta phi over delta T would be delta of this over delta T. And delta B over delta T, therefore, is equal to mu naught in delta I over delta T, which again is just using this first equation. So I should be able to substitute this in, noting that this is just n A delta B over delta T. And so I've got a delta B over delta T here, and I've got a delta B over delta T here. After some substitution, what I end up getting is n times A times mu naught times little n delta I over delta T. So going on to the next page, the induced EMF should look like n times delta phi B over delta T. And the induced EMF should look like negative L delta I over delta T. So if I divide these two by each other, or if I set them equal, like I have epsilon equals epsilon, these suggest that L delta I over delta T is equal to n delta phi B over delta T. And now substituting from the previous, our expression for n delta phi delta T, what I end up with is n times A times mu naught times little n times delta I over delta T. And so now I look at this and see I have a delta I over delta T here, and I have a delta I over delta T here. So that must mean that L is equal to all of this stuff. And so for the solenoid, I have that L is equal to, and let's go ahead and split this back into big N over little l. This becomes mu naught A big N squared over the length little l. We can do similar arguments for other things like a toroid. So with a toroid, remember the toroid is a solenoid bent into a donut shape. What you end up with is L is approximately equal to, not exactly, but approximately equal to mu naught times A times N squared divided by 2 times pi times R, where again R is like the radius of the donut. And you can do this with other things as well, although in actual practice, I think most systems tend not to lend themselves very well to an algebra-based approach. Even this one, there's a little bit that I'm kind of papering over to make it algebra-based. Most books have solenoid and toroid, and they may throw in one or two other things like a simple loop or a coax cable, something like that. But this is the basic process for figuring out the self-inductance for a circuit element. That's all that I'm going to do in tonight's video, so thanks for watching.